Hi, good morning, everyone. I'm George, and today I'm presenting you some design aspects of an arrow library to make it seamlessly asynchronous, so consistent with the rest of the ecosystem when the ecosystem supports asynchronous executions. Bit about myself: I'm George. I'm originally from Portugal, which is in Europe. I have a PhD in physics from a Max Planck, which is in Germany, from a German institution. I contributed a lot to open source, so for 10 years or something now in Django, Keras, Sphinx, Arrow, and a couple of others. I'm a co-founder of Munin Data, which is a small startup in Denmark, operating on the realm of the consulting space, operating in data engineering, data science, and consulting primarily on the biotech and pharmaceutical companies. And finally, I was a major contribution of Apache Arrow. Developed a lot of the Rust bindings for the Arrow implementation, including and also a lot of the infrastructure to support data fusion and to enable many of the data fusion use cases. I rewrote the bindings for Rust about 2 years ago for a major refactor, and since then I decided to contribute more to the Arrow part and to the Apache Arrow part of the project. So I've been working in Arrow outside of the Apache Arrow Foundation. So Munin Data, just to give you a quick introduction. So Munin Data was founded by myself and Nicholas Fish. So Nicholas is an 8-year ex-Microsoft that since then moved from US to Denmark. He has broad experience in software development, testing, and also extensive experience in data engineering and Hadoop installations. When Hadoop was a thing, now it's been focusing more into the cloud, but still the premise is still to provide access to the data with governance. While myself, I'm coming more from a scientific background, so data science, and then gradually been shifting a bit more towards data engineering, but more to the notion of making data usable and use the data in some form or another. And we've been operating primarily in the pharma space around regulated environments. So you can think like patient's data and clinical trials, so blinding and unblinding data, and also something called GXP, so GCP, which stands for good clinical practices, so how to execute data engineering processes in the context of regulated environments. That's primarily one of the areas where we've been working a lot. So coming back to the problem of designing an arrow library, I will need to introduce you three concepts before going to the main design choices. But before, and that's what I'm going to do now. So the first one that I want to introduce you is that information is represented, for myself, information is represented in four main categories. So you have the columnar-based format and the row-based format. And that you're probably familiar with, but the main difference is that in a columnar format, when you move to the bytes adjacent, so if you have an item and the adjacent bytes, they correspond to a different row, to a new row. In a row-based format, adjacent bytes, they correspond to a new column. Okay? The simplest way to see this is in a CSV file, right? In a CSV file, you have the headers, right? And you have the data that is comma separated. So you have bytes, comma, bytes, and those bytes, between each comma, there is a new column, right? So it is a row-based from this context. Another important axis or dimension in this categorization is whether the data is going to be, the information is primarily stored or primarily used or is primarily in use by a computer. So from this, and then the primary distinction here is that when you are having storage and in transfer, usually you want the data to be compressed, you want the data to be encoded so that you maximize compression. You may want to divide it in different files. While when you're in compute, you want the data to be well aligned with the instruction set that modern operating systems have, right? So that you can operate on them efficiently. This usually also means that you have random access at order 1, so you can easily access any element without having to decompress bytes and stuff like that. Okay, that's the 4 categories. So to give you some examples, CSV, Avro, flat buffers, they are example of storage transfer, and they are row-based. Then you have examples like Spark and Postgres, like the underlying compute model of Spark and Postgres. As far as I know, they are row-based. Then you have things like Parquet, ORC, Arrow that are on the realm of the storage transfer, but they are columnar. And finally, you have things like NumPy, Arrow, which are in the columnar format. They are in the compute. So just some examples, but just to give you the mindset is this, right? So these two directions on which we like to represent information, that we usually represent information. Besides information, there is an important aspect of analytics, which is the compute. And in compute, I like to divide it in two main sections. So the main section, and this is part number 2 of these 3 items that I want to introduce. In the compute, I usually like to divide it between CPU bounded and IO bounded. The CPU bounded are things that if you had a sufficiently large array that are passed through a function, that function will use your CPU 100%. So think about compression or decompression or decoding, hashing. All these are type of mathematics or arithmetics. All these are operations that if the computer can just take them all at this, like as fast as they can, and it will not sleep because of something. It will not have to wait for something. So that is what I called, like the examples are math, decompression, compression, and then you have another type of operations, and which I like to call them IO bounded. Okay, but it's a bit more generic than just IO. But the idea is this: you have operations that require you to wait, require you to sleep, require the thread to not do anything. So these are operations that even in the top performance on the CPU side, there are externalities that cause the thread or the core to have to wait for something. Okay. 2 examples of this is transfer of data. So blob storage is an example. Like you may have to wait milliseconds to get a column chunk from a Parquet file on the S3 or on the Azure Blob container. And you also have waiting for GPU. So if you have a process that is operating under performing a transformation that is being done on the GPU, you may need to send the data to the GPU. Then the GPU will have to perform the operation, and while the GPU is performing, the thread itself is just sleeping, or it's just waiting for the GPU to finish that operation, and then will continue. Right? So you have these 2 types of compute models or compute properties, and you can think that these are not these properties are properties of functions, like are properties of the API. So when you run an API, it is a property of whether it is CPU bounded or IO bounded or a mixture. Okay. So analytics as a discipline usually requires all the things that I just enumerated, right? So if you had 4 categories on data and 2 categories on compute, usually you end up with 8 categories that you need, that you use as part of your analytics engine. And a simple example, you may just use columnar and row-based or row-based, and then you skip 2 of the factor of 2 in the multiplications. Like if you're just using arrow or numpy, then you will always be on the row column, on the columnar-based. But then you still need to move across formats. If, for example, you have arrow and you write it to Parquet. So regardless, the point is that analytics requires both CPU bounded, IO bounded, because the transfer mediums are usually, you have some mediums that are more for transfer and the others that are more for compute. So to give you a simple example of why this is the case, let's place the traditional ETL problem. So you have a storage or a transfer mechanism. So for example, you have a stream of data that you're receiving, or you have a blob storage that you're reading from, and you need to perform some analytics on it. Well, the first step is usually you have to read it to memory. The second step is that you'll actually perform the operation on that data. And in memory here already represents something like in NumPy or in Arrow or in Spark model. So you'll have to perform some deserialization, also some decompression. Then you have you bring the transformation, you make the transformation, and you end up usually with a new in-memory format, because the output was optimized for the instruction set that you're using on your CPU or GPU. And finally, once you're happy, you will send it back to a storage medium or to transfer medium. And this can be, again, over the wire, HTTPS, if it's, for example, just an API response, but it could also be blob storage, Kafka, something like that. Right? So, and in this process, you will have a combination of CPU-bounded tasks and IO-bounded tasks, and formats that are storage transfer and formats that are in memory. Okay, and that leads these operations to intrinsically be CPU bounded and or IO bounded, or a mixture of both. So to give you a simple example, in the storage transfer, usually what you need to do is you need to read the data from that storage medium into memory, that is IO bounded, and then perform some CPU bounded operation to convert it to your in-memory format. So once you have those bytes, just a byte stream, then you need to convert that into your in-memory format. So for example, an arrow array or a NumPy array or a Spark struct, some stuff like that. So and that, for example, in Parquet, that usually needs, you have the page, the Parquet page, you need to decompress the page, so CPU bounded, then you have to decode the page, CPU bounded, until you are in your in-memory format. Okay, so and then in transformation you may also have IO bounded. So for example, if your transformation is having GPU calls, then you may have to wait for the GPU to run, and in that case, then you have an IO bounded call in the mixture, right? So analytics as a whole usually requires storage formats, in-memory formats, sometimes row and columnar, depending on the type of analytics you're doing, and then it requires CPU bounded and IO bounded tasks. Now, the challenge of this is that if you have CPU bounded tasks and IO bounded tasks, they behave very differently, right? They are just concepts but they express the notion that the CPU may block or may be fully committed to the task or may not be fully committed to the task. It's like it may be waiting. And in that case, asynchronous was a methodology that emerged to address especially the IO bounded type of tasks. And you can think that asynchronous is just an API to use an application runtime, so that it expresses the behavior of being able to declare tasks that can wait, that will wait, and that we can try to use the thread while it's waiting to do something else. Okay, so that's the basic. So the very simple the very simple understanding is you have an application runtime. The application runtime has a thread pool, so it owns a bunch of P threads, so operating system threads, and then the user of this API is able to push tasks to the application runtime, and then these tasks get scheduled to some threads. Okay, this is the NM problem, the NM model. So and I will just focus on this model because it's widely common in Go, in Rust, in C++, so I will just use it. The second aspect of asynchronous, and that most programming languages or runtimes implement, is the notion that async is often implemented via cooperative scheduling. Cooperative scheduling works as follows. So given that you have the basic idea is this: you have a task, let's say task 1, and I'm representing here the size of the task by the number of CPU cycles, right? So there is the arrow is just CPU cycles, and I'm adding these two black lines there. And I'm going to explain you now. So the task is composed by a bunch of CPU cycles, but between those operations, so you can think that the gray area is just CPU bounded, so it's just performing CPU bounded, and then it has these black lines, which the task is saying, at this particular point during the execution of the program, I may yield. So I may tell the scheduler, please, I have this P thread that I'm been running on that I may not need it right now. So please, you can use it. You can use it for other tasks. And so this task 1 is yielding the P thread to the runtime, and he's telling the runtime, please try to use this thread to something else. I'm pretty sure I won't need it for some time. And this is usually because the task 1 is just saying, well, I have this IO request, for example, that I just submitted to the internet, and I know that I will have some time that I will need to wait until we have the response back. So runtime from in some time, ask me again if I'm ready, and if I'm ready, I will tell you, and then you can allocate myself to the P thread. Okay, that's the main idea. Now, what happens is that if you have many of these small tasks with a lot of black lines, what they will be doing is that we will be switching between tasks and advancing these tasks as they are needed. Okay, but in CPU tasks, that is a bit more challenging, because a CPU task is something like this. So it is a task which does not have black lines, because it fully commits. Like if you have to hash a function, you are not waiting for anything. You're just hashing. Like you just hash some data. You're just hashing, right? You're not waiting for anything, and for that reason, you will not yield. You're just, well, you ask me to compute this, I will compute you, and I will return it. Okay. And you cannot use this P thread for anything else, because I will need this P thread anyway. So we may as well not even switch the thread and have the context switching cost. Okay, so that's the main idea. The challenge becomes that when you have tasks that are IO bounded and CPU bounded at the same time, from an analytics point, which we have in analytics as we just described before, then you have a challenge. And the challenge is that now let's look at these tasks in the time perspective. So as a user, as a real time clock wall time. In this representation, let's just consider these two scenarios. The first scenario is that the task 10 is executed first, and then the task 1 is executed, and then let's do the opposite. Actually, let's do the other way around. So task first, the task one first is going to be executed. So let's pick task one. If we had only one task and we execute task one, this would be a behavior of task one. So you have some CPU, so CPU usage would be 100% in the beginning. Then you have a yield, but you don't have any other tasks, so the runtime will just wait, and from time to time it will ask if the task one is ready. So while the task one is not ready, it's just waiting for I/O, and then when it becomes ready, you have some more CPU, then you have a second request, and then some I/O, and then some CPU work. Okay, so this would be the total time of task one. Now, what would happen if we had task one being executed and then also push task 10 to the runtime, saying, well, I have these two tasks, please run them both. And task one happens to start first. In this case, we will have something like that. For a single pthread, so if the runtime only has a single pthread, then we start task one. When it yields, the runtime says, "Oh wait, my task one is not doing anything with this pthread, so I will just assign it to this task 10 because it's available. Like I have it in the queue." So it just starts running task 10, and then once task 10 finishes, because there is full commitment, so the runtime cannot switch tasks. Then when it finishes, then we can move back to task one, and then task one runs for a bit more, then waiting, and then a bit more, and then the process finishes. Okay. So, and you can see here that we were able to perform concurrency work, right, by just saying that while task one is waiting, we can run the CPU task part, at least part of it, we can run it while it's waiting, and the other one, well, we'll just have to waste some time here because we cannot commit more, right? So from that perspective, this waiting I/O here, we have to use it. We have to just wait without being using the CPU. Right? So that is that is if task one started. But now let's take the opposite case. Let's take that the task 10 started before task one. In this case, this is what happens. So you have task 10, it committed the pthread, and then you have task one. So this I/O that we were just waiting, we can no longer benefit from this combination of CPU and task I/O. So you can see here, right, the task is also taking longer because now this waiting I/O that we could have used to do something else in this model, we cannot use it for anything else, right? And that is generally the problem, is that if you have many tasks scheduled and in analytics, especially if you have a lot of data sets or a lot of joins or a lot of Parquet files, then you end up with a lot of these small tasks, and then these tasks, they start competing with CPU tasks, and the CPU tasks just block, like they will just commit to the thread, and the other ones are not able to perform these small increments that take a long I/O time. Okay, that's the problem that Async solves, but this is the problem that CPU-bound tasks bring to the Async world. Okay, so this is the introduction. Now, going back to the design. So Arrow 2, so as I mentioned, there was I rewrote a large part, or essentially the whole library, Rust bindings of Arrow into a version, into a separate repository and a separate execution model. And Arrow 2 is a rewrite of the official Arrow of Light. It implements the full Arrow specification, so it's just the Arrow specification, and it passes all integration tests against C++ and Java, so it's it's complete in this sense. It's the backend of Polars, which is a fast data frame API in Python. So it's made by Hichi, which is a very talented developer, and a group of people that have been contributing to it, that essentially exposes, it's a bit like Pandas, but way faster than Pandas, and uses Arrow as their backing memory. So they switched from Arrow to Arrow 2, and since then it's been using Arrow 2. And the core design of Arrow 2 in the context of I/O, which is what I'm talking here now, is the idea that for every format, there is a separate API to read and to deserialize. Okay? And that's, by the way, it's the core design, and it's also what I recommend people to do if you're designing an Arrow library, is to separate APIs to read and to deserialize. Why? Because remember, those tasks, like the task of I/O bounded, we may need to run it in an asynchronous context, but the CPU bounded, we may need to do something about it to not starve the asynchronous runtime with these large blocking blocks. So let's do that. So for every format, there is a separate API, and then the read API has two variations. So we always offer an asynchronous version, And this is already to flag, like we have a bunch here of data, a bunch of operations here that are primarily IO bounded. So you will need to perform, we will need to interact with the blob storage or with the stream, or something like that. So so traditionally you would expect that to be run on an asynchronous context, but because not every API in Rust and in the world is supports asynchronous or wants to be used asynchronously, we also support you asynchronous API, so an API that does not have DL weight. And this is useful, for example, for local file systems on which the latency is usually very small, and therefore you don't benefit from asynchronous. But in other instances, you benefit from asynchronous. And then you have the deserialize API, and the deserialize API is always synchronous, okay? Which makes sense, right? Because the deserialize API is always CPU bounded, so there is no reason to make it asynchronous. It will just perform compute. That is the core design in the IO space. And what this allows is that, remember those two types of tasks, CPU bounded and task 1 and task 10, that is CPU bounded. It allows the developer to very granularly select how to schedule these tasks. So for example, do you want to use the same thread pool? Do you want to use different thread pools? Do you want to run the CPU bounded work on an asynchronous context, or you want to push it to another thread pool? For example, in Rust, it's very common to use Rayon for parallelization. So the one aspect of Arrow 2 is that the serialization API is parallelizable, is fully parallelizable. So this implies that, for example, to read polars is extremely fast in reading Parquet files, and I think it's currently much faster than PyArrow, like a factor of a third or a half or something like that. And the reason is that what it does is that it reads the column chunks as you usually do, so IO bounded, but then you run those column chunks in parallel. So you are deserializing all the columns, all the Parquet columns in parallel. And this makes it really fast because you just parallelize over the different cores that you have available. So that is the core design. So to give you some examples, well, this should have been a link, like here, like this one. I will just copy paste it and use it. So to give you some examples of how this works, let's start with a simple example using ND-JSON. So this is the repository, right? I'm not going very far with this, and in this case, I'm giving you. So this is you can see here, it's a 40 line of code example, and here you will see what I mean with let's decouple the APIs. So what I'm doing here, this is just a function that, given a path, it will read an ND-JSON file. An ND-JSON file is just a JSON file on which each line is a valid JSON. Okay, and it's a JSON format that's very suitable for streaming. So how does this work? Is you have a batch size, so you just decide how many rows you want to read per batch. And in this case, this is all synchronous. You can see that there is no async here. So what we do is we have a file reader. So we just read this. We just read the file in batches of batch size, and this thing here is just bytes. So we are just reading the bytes of the file, and then we have here a while let sum. So we are just iterating over this reader. And so what this doing is the read, the next is IO bounded. The read column deserialized is CPU bounded. And you see, I just decoupled this. So now, as a user, you can decide whether you want to do the IO bounded in the same thread pool, or even in the same process if you really want to go crazy. But you can just read that part and then deserialize it afterwards. So what you can do here is that, for example, this deserialization is usually CPU bounded, is pure CPU, and which means that, for example, you could have just read this with buffering. So you would just read 3 or 4 batches, and then you are deserializing, and you have a ring on which you are deserializing it with parallelism in place, right? So you're just deserializing the multiple chunks in a single go with parallelism. So, and this is allowed because you have this decoupling. So you know that when you call some API, you are just performing IO. When you call some the deserialization, you are doing CPU bounded. Okay, so this is an example. Coming back to another example, let's go here to Parquet, if I can press on it. Yes. So this example, we are reading Parquet in parallel. So we are reading a Parquet file, but the way we are deserializing the Parquet file is in parallel. Okay. So coming back to the main function, so again, 71 lines of code, so not very large, but what we are doing here is just give me a file path and a row group. Okay. And now we are going to read the Parquet file in parallel. So how that would work? So in this case, we have to read the chunks, the column chunks from this row group. So we select the row group, we say we have a given chunk size, we read the column chunks. So read this read column and is IO bounded. Again, it's a read, right? So you read underscore, so it is most likely IO bounded. And then you have a CPU bounded work. And what is that? Well, once you have the column chunks of your row group, you can just run through the iterator of the chunks, right? How many rows you want per chunk, and then per each one you will just advance the iterators of the columns. So these columns, you can think that they are just iterators, so they are bytes, so just bytes, and then you have some structs that are just binding to those bytes to know how to deserialize them. And then once you call next, it will start deserializing. So for example, the first thing it does is that it goes to the first page and it deserializes, decompresses the page into bytes, and then it starts decoding, right? And the important thing is that because these columns are we will need them all, right? For a chunk of multiple columns, we will need to parse all these columns. So what we can do is we can just iterate them in parallel. So this pariter is just fork these columns into multiple into multiple threads. In this case, p threads, because this is now using CPU bounded work, and then iterate. So advance each of these iterators by one. So you get an array per iteration. So in this case, you get n arrays, one per column, but the way that they are being deserialized is CPU bounded and is parallel. Okay, and this is, by the way, this is how Polars is actually also doing the reading of Parquet files in parallel. You can even do more crazy stuff than this, but the main point is that because we separated I/O from CPU bounded, you can decide when to do the I/O, which there is this risk that you are hitting an S3, and then you have to be mindful about it. But all the other CPU work, you actually don't care about that part. So you, from an I/O perspective, like it's just CPU. So let's just try to parallelize it. Finally, the third example, which is this Parquet read async. So I will just try to get into it. I think probably the easiest way is to just go to examples and go to Parquet read async. So in this case, we are using Asynchronous to do the I/O part of the work, and then we are running the CPU bounded work inside the async context. So it's not advisable, but this is just an example, right? So you can do smarter things by just moving it to a different thread pool. In this case, we are just running it in the same one. So again, 55 lines of code. Let's see how it goes. So the main, this is just a main function, right? So it just gets a file path. Then it creates a reader for that file path, and now it's an asynchronous reader. So this is using an asynchronous API that Tokyo provides. In this case, it's library specific to read files from the file system asynchronously. So this is usually just done during planning, but this is just reading the metadata. So you have one block. So remember these black lines that I mentioned in the tasks? These are the black lines. This await here. Okay. So what we are telling the runtime here is, well, if you have other tasks, please, I'm going to spend some time doing this operation. So just move to another task. And here again, because this is IO bounded, then this is still a mix of IO and CPU bounded, because remember that to read metadata, you actually need to deserialize the metadata, the metadata struct that is in drift into Rust, and that is still has some CPU, but this is O1, so it's a very small operation CPU. So we still move it to the async, so to the async API, so to the read API. Then this is just a technicality for Rust, but you can think what you can see here is it for each row in the row groups in the row groups in the Parquet file. Well, we just read all the columns to memory, and you can see here now a wait. So this one actually performs a fork of the column, so it reads the columns asynchronously. So if you have an S3, it actually performs n requests, where n is the number of columns in your Parquet file that you want to select. This none here is that there is no projection pushdown, so no projection. But if you're projecting these columns, then you would just get a subset. And of course, the second step, once you have the data in memory, again, is the same interface. So you can see here. Then in this case, we just want to iterate over chunks. So we actually can create a row group deserializer, which is just a small struct to be able to have this as a deserialization, and then this iteration, so the moving of chunks one forward, is the is the CPU bounded work. So what you could do is pick these column chunks, move it to another thread pool, and then perform this work on a separate thread pool that is not blocking the I/O. So you always have the I/O ready to perform these I/O bounded requests, so that you can switch tasks easily and have the tasks to be small increments towards the completion of the process. That was the three examples that I wanted to give you as to. Let me try to come back to this one. Yes, good. So this is the three examples that I wanted to give you. Coming back to the summary. So analytics uses I/O and CPU bounded tasks very often. So you have to think through that these are fundamentally different, because one of them is very prone to sleep, the other one does not sleep. Async via cooperative scheduling is only useful for I/O bounded tasks. So if you have pure CPU, you don't need async, and usually you should actually avoid, because it's more complexity to your code base. When you're designing libraries, and in particular arrow libraries, always remember that there is this aspect of I/O bounded tasks and this aspect of CPU bounded tasks that users may want to run on a different thread pool or in a different way. So just give them that flexibility, because that flexibility will be extremely useful for them. The risk of not doing that is that the applications that users developed on top of your library will be designed mixing these two things together, which causes the application itself to perform subpar to what an asynchronous context enables, because of that thing that I just mentioned, right? Because if you have two tasks on which one is CPU bounded, the other is IO bounded, you may end up executing the CPU bounded task for the duration of the period, and then you lose that IO bounded period that you're just waiting for IO calls to complete. Yeah. And finally, if you're a user of a library, always think through what is the trade-off when executing CPU I/O. Like, is it worth to introduce a runtime, an asynchronous runtime, because of this problem? And if yes, then how are you going to push the CPU bounded tasks away from the async runtime so that you don't block it? Or what mechanisms do you use? So always think through this also as an application developer, that whether the library provides you the opportunity to do that. With this, I would like to thank you very much for your time, and I hope you enjoyed also the other sessions. Thank you.